Hey guys, different math video from normal here. Normally my videos are speedrunning and gaming and the like, but I was studying maths and looking at math literature, watching maths videos, and I realized we have a kind of crisis in the complex numbers as no one proves anything. So, I decided to take initiative myself. And that is that you constantly hear, especially when you start talking about complex functions, that a complex number squared will be the magnitude squared of the original complex number, and it will be moved, the angle relative to the positive real axis will be multiplied by 2. You hear this all the time, and it's a really easy way to think about the transformations geometrically, but proving them, not many people do. So, here's my chance. Functionally, we're going to be looking at the first part first, and the second part of this video we're going to be analyzing the 2 times the angle assumption. First, let's prove that the magnitude of some original vector squared, some imaginary vector squared, will be equal to the square of the original magnitude. If you don't remember what this is, basically assuming A is our x vector and B is our y vector, we are going to be looking for the square root of a squared plus b squared. This is the magnitude vector for just a plus bi. Since this is squared, we're looking for functionally the magnitude of a new vector, our original vector squared. We are looking to prove that it is equal to a squared plus b squared, because square root of a squared plus b squared squared is equal to a squared plus b squared plus b squared. Now, the first step in analyzing this is to simplify this. If you remember, any a plus bi squared will simplify down to a squared minus b squared plus 2abi. Now you can see, when you write it down like this, that this is our I hat, our horizontal vector. And this, because we have an I attached to it, is our j hat. So, we can write this resulting vector as this magnitude as the square root of a squared minus b squared squared, I hat, plus 2ab squared. Remember, we dropped the imaginary number because this notation is simply representing j hat. We're not using square root of -1 anywhere in this calculation for the magnitude. And we are looking to find out it's equal to a squared plus b squared. Now, let's simplify this a little. This term here, if you do the work yourself, you'll see it expands to a to the 4th plus b to the 4th minus 2a squared b squared. And this term expands to 4a squared b squared. All of that underneath the radical is equal to a squared plus b squared. We can simplify this. We see that these two numbers here, -2a squared b squared and 4a squared b squared, have the same coefficients, a squared b squared, so we can simplify the integers here. This gets us the square root of a to the 4th plus b to the 4th plus 2a squared b squared equals a squared plus b squared. Now, we can simplify this as the square root of a squared plus b squared squared equals a squared plus b squared. Since we're squaring the entirety of some number underneath the square root, we can just drop that square root and drop that square to get us a squared plus b squared is equal to a squared plus b squared, showing that the magnitude of a vector squared is equal to the square of that original vector's magnitude. Now, to address the second aspect of squaring a complex number that's usually glossed over, is that the angle of the original complex number squared will be equal to 2 times that angle. This angle function notation is basically just saying the angle that we get. Now, normally you can define this very easily if you've had trig, but I'm going to assume that you haven't had much trig experience, so I'm going to try to define it for you. You do need to know what the unit circle is, though. Let's analyze this function right here, this angle function. Now, we know that if you divide the vector you get, both parts of the vector, by the magnitude that you get, you're going to get something on the unit circle. Or at least I'm going to assume you know that. So, we can write this as having 2 important properties. Our theta, or our angle, of a plus bi will contain the property that the cosine, the measure of the horizontal element of a unit circle at any angle theta, the cosine of the theta is going to be equal to a divided by the magnitude. Now you may ask why this is the case. This is because if you remember SOHCAHTOA, cosine are adjacent divided by our hypotenuse, which in this case the hypotenuse is the magnitude of the vector. This holds true. We know that cosine of 2 theta is equal to 2 cosine squared theta minus 1. If you need to refresh yourself, you need to go over some trig identities, some site like Purple Math, please do so, because I hope for your own sanity that you have not memorized all these trig identities. Also, let me make this clearer. This doesn't look like a number, nonetheless, 2. One last thing. Because of our assumptions here, that our theta of the number squared is going to equal our 2 times our original theta, this means that we're also going to assume that cosine of 2 theta equals a squared minus b squared over magnitude squared. Now you may be asking, what just happened? Why did we bring a b term into this? Well, remember, if we square a plus bi, we're going to get a squared minus b squared as our real component, as our I hat component, which means that we have to attribute the horizontal position of the vector as this. And because we're squaring it, that means this m squared naturally comes along for the ride. Because 1 over m times 1 over m equals 1 over m squared. Now we can start proving. So, we're going to be using a ton of substitution. I'll be putting notes, hopefully, in the description to help keep things on pace if you get a bit lost. So, 2 cosine squared of theta minus 1, we know, is going to be equal, because this is equal to that, is going to equal a squared, not minus, oh, you make a dangerous mistake if you accidentally put a minus, let me correct that, is equal to a squared minus b squared over m squared. Now, we can say, because we've already defined cosine here, that 2a squared over m squared, because a over m times a over m equals a squared over m squared, minus 1 equals a squared minus b squared over m squared. Now, if you remember, our b value can be written as, because of the way this is written as b equals the square root of m squared minus a squared. You can think of this as trying to find the leg, not the hypotenuse, of a right triangle, where you know the hypotenuse and you know one other leg. Which means we can simplify this down to 2a squared over m squared minus 1 is equal to a squared minus m squared, remember this is negative, plus another a squared over m squared. Next, you've already simplified this in your head, you've already solved the proof. 2a squared over m squared minus 1 is equal to 2a squared minus m squared over m squared, which means 2a squared over m squared minus 1 is equal to 2a squared over m squared minus 1. And just to be professional, the proof is complete. This means now, if you ever have any complex number, you can find out what its square is by squaring the magnitude and by doubling the angle relative to the origin, or the positive real numbers.